A popular theory in certain circles suggests that the reality surrounding us is nothing more than a computer simulation created by more advanced beings. Recently, with the rapid development of virtual reality and artificial intelligence technologies, scientists and notable figures acknowledge the possibility that our world could be artificially modeled on an immensely powerful computer. According to the estimates of many specialists, computational capabilities of computers are expected to grow by millions of times in approximately 100 years. Thanks to this, we will be able to create virtual worlds so realistic that their characters will essentially acquire consciousness, but will remain unaware that they live in a simulation. The hypothesis of the virtuality of our world was first widely presented in 2003 by philosopher Nick Bostrom. He suggested that if there are numerous sufficiently advanced civilizations, they may create simulations of the universe or its parts, and we are likely living in one of them. Bostrom hypothesizes that, in the future, our civilization will reach a level of evolution where technologies will allow the creation of modified individuals with unlimited mental and physical abilities. They will be able to model simulations indistinguishable from reality, similar to what was depicted in the movie The Matrix. Inhabitants of the virtual world will possess the same intellect and psyche as us, consider themselves biological beings, and believe they live in the real world. But is it possible to endow them with consciousness? According to Bostrom, the mind and intellect can exist outside biological brains and can be artificially recreated on other physical carriers. Currently, this sounds unrealistic as scientists have not yet unraveled the workings of brain cells, but the philosopher does not deny that this will happen in the future. When computational technology reaches the necessary power, people will be able to replicate brain cells electronically. This theory is actively promoted not only by scientists, but also by public figures. Tesla and SpaceX founder Elon Musk stated that humanity is on the path to creating reality indistinguishable computer games. Therefore, the probability that we are in the base reality is 1 in a billion. According to Musk, we have two possible outcomes. Either we create reality indistinguishable simulators, or civilization ceases to exist. Humans perceive the surrounding world through various sensory perceptions such as hearing, vision, touch, smell, and taste. However, there arises a question of how certain we can be that our current state is not a dream and that we are genuinely in a waking state. In the late 20th century, philosopher Hilary Putnam described his thought experiment called brain in a vat, in which he could demonstrate the illusory nature of our perception. The idea of the experiment was that the human brain could be extracted from the body and placed in a vat with nutrient solution, then connected to a computer that would emulate neuron activity. Electrical impulses, similar to those occurring in a real body, would create the illusion of perception. Thus, the computer could create virtual reality while the brain continued to perceive itself as alive and the surrounding world as real. According to the philosopher's reasoning, it is impossible to assert with absolute certainty that the reality we perceive is objective because such a claim is based only on belief. Several theories confirm the existence of virtual reality, with many stemming from quantum mechanics. Navigating through an open-world game, we observe a bustling city life. In reality, cars and pedestrians only appear on the streets where the player is present. Other locations are simplified or not loaded at all. This principle is common in all games to prevent computer overload. Virtual reality exists only where our gaze is directed, and the observer influences the game world merely by their presence. The observer effect is common in games, but a similar phenomenon has been observed by physicists in real life. The results of the double-slit experiment by Thomas Young and his followers shook the world and altered our understanding of science and reality. Quantum objects change their behavior when observed. To understand the essence of this unique experiment, let's look at the behavior of particles. If we shoot small solid balls at a screen with a slit, we see a single stripe on the screen where they hit. Adding another slit results in 2 stripes on the screen. Now let's examine how waves behave in this scenario. Passing through a slit, waves spread, hitting the screen along the cut with the greatest force. However, when a second slit is added, something amazing happens. Meeting each other, wave peaks lead to their cancellation, creating an interference pattern on the screen with multiple stripes. The point where wave peaks collide provides the highest impact force, forming bright stripes, while areas where waves cancel each other show no visible manifestation. Thus, passing solid balls through 2 slits, we see only 2 stripes, while with waves, we observe a unique interference pattern with multiple stripes. Now, let's consider photons, the smallest particles of light. Passing them through a single slit produces only 1 stripe on the screen, similar to the solid ball experiment. However, when we pass photons through 2 slits, something incredible happens. An interference pattern appears on the screen with multiple stripes. We released photons, the tiniest particles of light, hoping to see only 2 stripes, but instead, we encounter a variety of stripes, similar to those generated by wave interference. Later, scientists found that not only photons but also electrons, protons, and various atoms exhibit the same strange behavior. In an attempt to eliminate interaction between microparticles, physicists released them one by one to exclude the chance of collision. Yet, an interference pattern appears on the screen again, violating established physical laws. Logic suggests that a particle, as if splits into 2 parts, passes through both slits and collides with itself. In a desperate attempt to find out through which slit the electron passed, physicists install a measuring device at one of the slits and release an electron. However, quantum mechanics has more mystique than scientists could imagine. When they began to observe, particles started behaving like small balls again, producing an image of 2 stripes instead of an interference pattern with many stripes. So, the act of measurement or observation of which slit the electron passed through revealed that it passed through 1 slit, not 2. The electron decided to behave differently, as if it knew it was being observed. The observer disrupted the wave function of the particle merely by the fact of observation. One key explanation for the mysterious behavior of microparticles in the double-slit experiment is the many worlds interpretation. The essence of this concept is the assumption that parallel universes may exist, each with the same laws of nature. According to this theory, with each act of measurement, the quantum object's observer, in a sense, splits into several versions. Each of these versions perceives its own measurement result and operates according to this result in its unique universe. Another hint at our possible existence in a simulation can be found in the fact that our universe has a maximum speed that is scientifically unexplained. According to Einstein's theory of relativity, nothing can exceed the speed of light in a vacuum. However, as the speed of an object increases, its time slows down, a phenomenon confirmed by various experiments. This could be interpreted as a result of information processing, updating the virtual reality. Virtual reality, like our universe, may depend on virtual time, and increasing speed may affect processing cycles, leading to time dilation. Evidence that we might be living in a matrix can be found in the phenomenon of quantum entanglement. Consider a microparticle, such as a photon of light, traveling in space. This photon possesses a property called spin, essentially representing an upward or downward rotation. Research from the double-slit experiment concluded that until the moment of observation, the photon doesn't have a definite spin. The photon flies in a superposition of uncertainty, as if nature finds it challenging to precisely predict the rotation of each elementary particle. Only after observing the photon is a specific spin attributed to it. This means that the observer influences the particle's properties, making it physically more complex. When a cesium atom emits two photons in opposite directions, their states become entangled due to quantum entanglement. This implies that if one photon spins upwards, the other must spin downwards, and vice versa. Einstein proposed an experiment to test the correctness or incompleteness of the Copenhagen interpretation of quantum mechanics. If a measurement is made on one of the entangled photons to determine its spin, the second photon instantly changes its spin to the opposite, even if it is far from the first. This causes confusion, as according to known laws of physics, nothing can move faster than light. Einstein suggested that information about the photon spins is pre-existing in them before measurement. However, over time, it became clear that quantum mechanics contains more mysteries than Einstein himself had anticipated, and his viewpoint turned out to be erroneous. After the widespread dissemination of the theory, many people began to seek evidence that the surrounding world is an illusion. All mystical and paranormal phenomena that science could not explain were attributed to the category of glitch in the matrix. This category included déjà vu, a state in which a person feels like they have already been in a certain place or situation, but cannot recall the details. Today, despite significant progress, science is still unable to provide a precise answer to the question of whether we and our world are products of the matrix. It is possible that, in the future, scientists and philosophers will be able to confirm their theories in practice by creating the first matrix analog, a simulation that will not differ from reality. However, this may take hundreds or perhaps thousands of years. As Nobel laureate and father of quantum mechanics Niels Bohr once said, "Everything we call real is made of things that cannot be regarded as real." If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet.